you've already heard about the double copy, and Zvi already introduced the double copy, I think, last week. And probably you saw hints of it in Yaroslav's lectures as well. So what I'm going to do is build on that foundation. First of all, I'll talk a little bit about, just how the double copy works. And then I'll start talking about more the connection of the double copy to current excitement about gravitational waves, so classical aspects of the double copy. And finally, I'll talk about some relations between the double copy and some of the sort of more characteristic solutions of general relativity, exact solutions, the Kerr black hole and things like that. So that's sort of the basic outline. I kind of have a bit of a syllabus or a plan for my lectures. That's right. So lecture 1, that'll be today. I'll talk about color kinematics. So this is one of the key aspects of the double copy. Lecture 2, which I think is also supposed to be today, I'll talk about states. States of the double copy. There's some sort of, interesting things to say about those, I think. In my third lecture, let's see. Classical observables. Things get a little bit more vague after this. But I'm planning to talk about gravitational waves from the double copy in lecture 4. And then finish with exact solutions. Okay, so, well, since you've already heard a little bit about the double copy, I don't want to spend a lot of time explaining why I think it's an interesting thing to talk about. Still, it's worth saying something, right? The double copy is a remarkable new point of view on gravity. It's quite a shocking thing if you think about gravity from a geometric point of view, a curvature in space-time and things like that. The double copy is totally different, right? It says, oh, you don't think about curvature in space-time at all. You think about Yang-Mills theory, or you think about some simpler theories which you can somehow upgrade to extract physical predictions in gravity. And the advantage of this is, well, one advantage, of course, is it's a new point of view on gravity. And gravity is one of the most interesting aspects of physics. No matter what you think about in physics, most of our main problems are somehow connected to gravity, right? How do we think about gravity in the ultraviolet? How do you think about quantum mechanics of black holes? There are many, many questions. So it's very interesting that double copy just provides a radically new perspective on on gravity itself, on the basics of gravity, right? But it's still great that the double copy then has a direct impact on a subject which is very exciting right now, which is data. That's always been very beneficial for people working in scattering amplitudes, as we tend to make a lot of progress on something when there's some data out there, something that forces us to do a computation. And when you figure out how to do that computation, you often learn something. The double copy is an example. I think Zvi found the double copy with Henrik Johansson and JJ Carrasco because they were doing a hard calculation, and then they noticed, oh, look, this thing's happening. It's simple. It's cool. Okay. So the double copy is a new point of view on gravity, but there's a saying in particle physics, which I think goes back to Bryce DeWitt, which is that the only observable in gravity is the S matrix. So the S matrix, of course, are the amplitudes. What this slogan of some sort is supposed to tell you is that if there is something you can observe in gravity, in asymptotically flat space, then it must somehow be connected to amplitudes. Since the amplitudes can be computed from the double copy, the slogan is trying to tell you that everything you can observe in gravity is somehow related to Yang-Mills theory. And in part, that's what I'm going to talk about. The gravitational waves is one example, exact solutions is another example, and maybe I'll touch on some others throughout these lectures. Okay, so please do interrupt me if you've got any questions. These are supposed to be lectures, so put up your hand or just shout out, and I'll answer. Okay, so let me begin with color kinematics. All right, so the statement of the double copy, or the BCJ form of the double copy. So the way people often state this is, if you give me an amplitude in Yang-Mills theory, I'll call this A. So I take this amplitude, I write it as a sum over cubic diagrams. So that's diagrams with just 3-point vertices. So I call those cubic diagrams. And then the expression for each diagram is the following. So there's a numerator here, a kinematic numerator. It's made out of polarization vectors and momenta. There's a color factor, which are made out of all these FABCs that you've got in Yang-Mills theory. And then there's some bunch of denominators, the Feynman propagator denominators, which you read off from the cubic diagrams, right? So now, if you just take the Feynman rules in Yang-Mills theory, you'll get a 4-point diagram, right? But that 4-point diagram you can rewrite in terms of 3-point diagrams. And I think this might have been something Zvi talked about last week. Okay, well, now, given such an amplitude, then the amplitude in gravity is written in the same way, sum over cubic diagrams. But I replace the color factors with another copy of the numerator. Now, so this is the double copy. It holds provided anytime the color factors satisfy some Jacobi relation, Cj plus or minus Ck equals 0, then the numerators satisfy, the same relation. Okay, so, and then really this is the part that's somehow color kinematics. So the idea here is that the kinematic numerators, these n's, satisfy the same algebraic properties as the color factors, the C's. Right? Okay, so let me say this is color kinematics duality. Okay, now just some remarks. So these numerators don't have to be the same. That could be a numerator in a different theory, for example, pure Yang-Mills, and then Yang-Mills coupled to some matter, some fermions, for example, or some scalars in the representation R, or it could be a supersymmetric theory. I'm ignoring factors of couplings here, just to make my life a little bit easy. So if this was a tree diagram with n points, then there would really be a factor g to the n minus 2 here. And here there would be a factor kappa over 2 to the n minus 2. This kappa is the gravitational coupling that we tend to use, basically the square root of g Newton up to maybe some factor. And there can also be various factors of I running around here which you might have to worry about. Those are convention dependent. So I'm just going to ignore them. Okay. Now, so color kinematics is sort of an amazing thing, and you might wonder, where on earth is it coming from? Right? Why? Why? I mean, obviously, this is very suggestive. It makes it look like there should be some algebra, something like a Lie algebra, or something that's cooking up these kinematic numerators. But we can understand the origin of color kinematics, of color kinematics duality. Well, we can understand the origin arising from gauge invariance. That's one point of view in it, right? It's maybe not the most fundamental, I'd hope not. Understood. Okay, so to see how this works, let's see how amplitudes turn out to be gauge independent to begin with, right? So I'll start with Yang-Mills. In a way, that's supposed to be where you start when you're thinking about the double copy, right? So I'll start with Yang-Mills. Okay, so now, these numerators here depend on the polarization vectors of all of those gluons in your Yang-Mills amplitude. Right? So I can just pick one of those polarization vectors and perform a gauge transformation on it. So I'll select some particle. Let's say its momentum is p. Right. So performing a gauge transformation means I change the polarization vector. Gauge. So the polarization vector of this particle, I'll call that polarization vector epsilon, it gets replaced by another polarization vector epsilon prime, which is just the original epsilon, and then you get to add a bit, plus alpha p mu, where this alpha is any number you want it to be, like any complex number. Okay, so this is a gauge transformation of the polarization vector, and certainly if I perform that gauge transformation, the amplitude in Yang-Mills theory is going to be unchanged, right? That's the word identity if you want. However, the numerators in general will change, right? If you've ever computed actual numerators for amplitudes in Yang-Mills theory, they're these complicated things. They've got dot products of polarization vectors with polarization vectors, dot products of polarization vectors with other momenta. It's just sort of quite a messy thing. And if you come along and you change one of those polarization vectors and you just do this to it, well, all those numerators change in some quite messy way, right? So the numerators change. So these ni's will, under this gauge transformation, become some ni prime, which is ni plus some delta I. Right? It's because I'm just, because I replace epsilon prime with epsilon. Right? There's some factor where you just get the same numerator as before, but then there'll be this delta which involves this alpha. Right? So this thing will depend on the alpha. Right, and these delta i's are not, in general, 0. Okay, so, but nevertheless, it's certainly true that the amplitude is gauge invariant, right? So that means that the amplitude, which was the sum, I'll just call my diagram I, right? Well, it'll be ni prime ci over di. I can use ni prime as much as the ni's. Ni prime is ni plus delta I. And since this is gauge invariant, this is equal to the original guy. Right? So in other words, it has to be, just by subtracting these two equations, it's got to be that this delta I satisfies a constraint. Sum over I, ci delta I over di, that has to be 0. Right. Okay. Now, this has to hold no matter what gauge group you're working with, right? It could be SU2, it could be SU8, it could be E8. It could be any group you want, SU of a very large number, right? And the point, what that means is that, you see, these CIs, I mean, if you were to type this into a computer, for example, and ask, is it going to hold? Well, the CIs will take on different values in all these different groups, right? So this doesn't just hold because the CIs have particular numerical properties. It has to hold on the grounds of the properties any CI has, any set of color factors, right? So what are the properties that we're sure that color factors always have? Right? Well, they're the properties that come from group theory. Right? Let me write something. This must hold for any gauge group. So it holds because of the algebraic properties of any color factors. All right, so what are the algebraic properties we can expect? So, well, there's basically two. Right? So the first is a set of Jacobi identities. So let me draw this out. What does a Jacobi identity look like? Okay, so here I'm going to imagine that I have a 4-point, or this sort of a propagator. Sort of 4-point type propagator stuck inside some larger Feynman diagram, right? So these blobs here can be, well, it's not really a Feynman diagram, some sort of cubic diagram, right? So these blobs can all be attached to some complicated diagram, right? And let me give these blobs labels, A, B, C, and D, right? So a Jacobi relation looks like this. Blobs, and another one, blobs. Okay, so it's useful, the good way to think about a Jacobi relation is you fix one of the blobs and you move the other ones around. C, A, B, A, B, C. So that's just a pictorial representation of a Jacobi relation. You always fix one thing and then you cycle the other three around. Then you get 0. That's a Jacobi relation. So color factors will always satisfy this because of the Jacobi relations that come out of the Lie algebras. And the second, there's a second property that we can always rely on, which is anti-symmetry. Anti-symmetry. So again, and just in terms of some blobs, if I have A, B, and C, well then I'll get a minus sign if I move to. So C, B, and A. Okay, those are the two general sets of algebraic properties we can expect of any color factor. Okay, good. So this equation, I'm going to give this thing a box and call it equation star. So this thing holds for these reasons, right? So, if you were to type this into Mathematica and teach Mathematica these relations, then you'll find that any time you make a gauge transformation, indeed, the equation holds, right? Okay, great. So now let's think about the double copy. Perfect. So, okay. So in the double copy, well, we started with an amplitude M, which was a sum over cubic diagrams Ni tilde over Di. Right? Now what I could do is perform a gauge transformation on this Ni. So under this gauge transformation, gauge transform, you will get some Ni plus delta I, Ni tilde. So I'm just touching the Ni's over Di. And now I want this to be equal to M. Right? As we certainly, if we start out with some computation in Yang-Mills theory, you don't want to say, oh, the double copy only works because you pick a very special gauge. So the double copy should work more generally than that. We don't control what the initial numerators are. So we want this equation to hold. Right? It will hold. This will hold, provided the sum over I, Ni tilde, delta I over Di equals 0. Well, when is that going to hold? Well, it'll hold provided the ni tildes satisfy these two properties, right? Because it was only these two properties that we needed to show this equation, right? So if ni tilde has the same algebraic properties as the Ci, then you're guaranteed to get a gauge invariant amplitude. Provided ni tilde satisfies same algebraic properties as the Ci's. Okay, so in other words, anytime the Ci satisfy a Jacobi identity, well, then the Ni's better do too. The anti-symmetry property is somehow kind of more or less built in. I mean, our Feynman diagram, that's easy somehow. So the interesting thing is the Jacobi relation. Okay, so that's one way of understanding where color kinematics duality comes from. Are there any questions on this? Yep. Ooh, yours first. Yeah, that's right. So yeah. So the observation, I'm not sure if it's a question. The observation was that the logic here is that we want we want the double copy to work. So therefore these Jacobi relations come out sort of as out of the logic that way. But it doesn't explain where they come from, and that's exactly right. We don't really know where the Jacobi relations come from in a more fundamental sense, although there are examples where we know where it comes from, and I'll give you an example. That's kind of what I'm planning to do in the rest of the lecture. But one of the major outstanding questions in this field, which maybe one of you will figure out, or some bunch of you collaborating together, is where did the Jacobi relations really come from in general? We don't know. And there's a lot of work on it. I mean, some people spend a lot of time thinking about these things, but there are interesting things that people say about them, but there's still not a good answer to this. No. Yeah, so that's a major question. Good. There was another question. Yep.
Yeah. So if I have some like 5-point diagram,
yep.
I have like a sum over many diagrams
yep.
here, is it that any subset of 3 will satisfy?
Yep.
Jacobi? That's
yep.
Okay.
Yep. So that's if you've got many diagrams, then the requirement is always that some subset of 3 of them will satisfy Jacobi identities. Yeah, so anytime there's some bunch of color factors that satisfy Jacobi identities, it'll be embedded in some very big diagram, then some bunch of 3 of them will add up and give you 0 with some appropriate signs. Great. Yes? Yes. No. So the question there is that, so there's a statement that if you want the double copy to work, only one of the numerators needs to satisfy these Jacobi relations. The other set doesn't need to satisfy the Jacobi relations, right? Now the logic there is, suppose you start with an amplitude and gravity, and both sets do satisfy color kinematics duality, right? Now, so both ni and ni tilde all satisfy the Jacobi relations independently of one another, right? Well, then what I can do for the ni's, for example, is make a gauge transformation like this, right? Now my new ni's, the ni primes, I've messed it up, right? So they don't have to satisfy the Jacobi relations anymore. Yeah. Okay. That's a good question. Yeah. Any others? Okay, excellent. Okay, so I wanted to make just a few quick comments, and then I'll discuss an example where we actually understand in a more sort of detailed way where the Jacobi relations come from. Yeah, okay. Okay, very good. Yeah, just remarks. Just a few remarks. One. All right, so one remark. I focused here on amplitudes with gauge bosons, right? Amplitudes basically in pure Yang-Mills theory, or some friends of it. So I was focused on cases where, let me see, I guess what I'm trying to say is that the color factors, or things like bunches of structure constants strung together, blah, blah, blah. So in other words, stuff where the color factor is all associated with the adjoint representation of the gauge group. So more general possibilities, more generally, you can consider some theories, and these could be relevant for gravitational wave physics, for example, with matter. So in some representation, some arbitrary representation, right? I like to think about these, well, the way I like to think about them when I'm thinking about more gravitationally wave type things is maybe some scalar particles, which I'm going to think about somehow as being black holes, for example. So some scalar particles with some mass and some representation, right? That could be a nice thing to think about when you want to discuss black holes. I'll talk about that more later. Now, what this means is that you're going to have other kinds of color factors, right? So you get color factors. You get color factors involving, TAs and TBs, and maybe they can have FABCs as well, blah, blah, blah. Right, so now you can have a more complicated system, right? Now, these color factors will still satisfy various algebraic properties, right? And again, if you've got gauge bosons connected to those, well then the gauge, outgoing gauge bosons, then this argument will go through essentially unchanged, right? You'll need to have gauge invariance. The gauge invariance will hold provided, for any representation, the gauge group. It will hold then based on the general algebraic properties of all these color factors. You can double copy provided the numerators satisfy all those general algebraic properties, right? But the algebraic properties now will be a little bit different, right? Because they'll have adjoint matter. And I'll do an example of that in a little while. It's maybe something that's not as well explored. It's maybe worth saying, so this BCJ story is proven at tree level. So this story here, it's known how to find numerators. There's an algorithm. Maybe Svi mentioned that, probably did. 3, there is a loop level generalization. Which I suppose in hindsight is somewhat obvious. So the loop level statement is, if you have an amplitude, let's say with L loops, so I'll just put a subscript L here for an L loop amplitude. Well, then I can write that as, let me see, so there'll be an integral now. Well, there'll be a sum. All right, let me start. There'll be a sum over diagrams. So we still sum over the same topologies of diagrams, so diagrams with 3-point vertices. The big difference now is that you have loop integrals to do. So at L loops, you'll have d times big L loop integrals to do. So there'll be a 2 pi to the dl. There'll be a symmetry factor for each Feynman diagram. There'll be numerators that now depend on loop momentum. So that is the L loop amplitude in Yang-Mills. And the idea is that we can double copy that in exactly the same way. So there'll be an L loop amplitude in gravity, a sum over I, an integral ddl, 2 pi to the dl. Same symmetry factor, because it's associated with the diagram, but now two numerators, right? Big difference is they all depend on loop momentum. That's a very big difference. Makes things harder. This is conjectural. Personally, I think it's certainly true, but maybe I'm an optimist. Anyways, this is certainly a good idea, and Zvi and Radu and folk have used this at high loop orders. You can direct your questions about that to them. Like, I've gone no higher than 2 loops. Okay. Okay, let's see, anything else I wanted to say? Yeah, okay, those are the remarks. Okay, good, so let me then move on to an example where we actually know how to make the double copy more or less explicit. So this is in the self-dual theory. Let's see. Self-dual. Okay, now the self-dual theory, this is just a fancy word to say that instead of scattering general Yang-Mills waves, which have helicities plus and minus, that all I will do is scatter Yang-Mills waves of one helicity, say helicity plus. Right? Yeah, plus, say, I mean, it could be minus. Just not both. Right, now you can't stop me from deciding to do that, right? Because I can just, imagine I make, well, yeah, this is a very theoretical world where I have machines that will generate gauge bosons of particular helicity for me, but I can just switch those machines to generating all plus helicity and scatter only those, right? So the diagrams will then look like this, I mean, I'll have some particles with lots of pluses. That's the kind of class of diagrams I'm going to think about. Now, it happens that the amplitudes in a theory where you just have plus helicities are very simple. In fact, mostly they're 0, but not all amplitudes are 0. But not all. Now, that of course means that things are a lot simpler, and maybe that's why this thing goes through so nicely. Now, very good. Okay, since there's only one kind of helicity, you'd expect that you can describe this system by a scalar equation, basically, some sort of scalar theory, right? I mean, there's this story, and people talk about that in Yang-Mills theory, we use A mu's, which have in 4 dimensions of 4 numbers in them, to describe 2 helicities, helicity plus and minus. And this forces us to introduce gauge invariance, and blah, blah, blah. And of course, all of that's true. That is true if you want to use a formalism where Lorentz covariance is manifest. Right? But if you don't care about that, if you're willing to use a formalism where Lorentz invariance isn't manifest, well, then you can write expressions for Yang-Mills theory that only have, that really have 2 scalar fields in them. In the self-dual theory, we set one of those scalars to 0, one of those scalar quantities, and we're left with one left, only one. So can describe. So I can describe this theory. Well, essentially using one field, one scalar. So in order to do that, you have to violate Lorentz covariance. Right? So I'm now going to give up Lorentz covariance. Right? So I will choose a set of coordinates, which let me see. I will try to get correct. So. So I'll choose coordinates. So there'll be a u coordinate, which is t minus z, v, which would be t plus z, w, x plus I, y, and then W bar x minus IY. Okay, and I can also then choose a gauge. That makes my life simple. So I will also choose the gauge AU equals 0. Okay. Very good. So now, I want to constrain the dynamics of this theory so that there's only one kind of helicity propagating, well, one kind of helicity external state. So to do that, I will impose the self-dual equations. So the self-dual equations then, so star f is I times f. Yeah. So star here is this Hodge star, right? So it's just some epsilon mu nu rho sigma acting on f mu nu. You know, some indices contracted is I times f, right? Make this factor of 2 in there. And I'm working with the convention where f mu nu, yeah, this is stuff you know. There's a minus here in this convention, it doesn't really matter. Anyway, so that's what a field strength looks like. Okay, maybe I'll go over here. AU, this is the U component. I chose the U component, yeah, so it's just one component, the U component's associated with this t minus z direction. And I'm setting that one to 0. Yeah. Good, yeah. What did I do? Okay, so now the self-dual equations, and I'm going to leave this for as a little bit of an exercise. So you can show that the self-dual equations imply, this is basically the component form, right? So there's 3 equations. So one of them is FUV equals 0. The second of them is now let me see, that can't really be quite right. Well, let me see. FWW bar. I might need to remind myself of one of these ones. FVW bar. So there's some indices there which are currently question mark. Ah, maybe this is FUW. Ah, that makes sense. And then this is FUV. Okay. So those are the. So this just means you take those star f equals IF equations, write them out for a little bit. Write star f as a half epsilon on f. Use these UV and W coordinates, and then you'll find that you get these 3 equations out of them. That's all there is in them. Okay, but now we can take these apart to learn about the dynamics of our theory. Yeah. So what we'll find is, so now remember what FUW is, right? It is, the F is over there. It's some derivative of, this is du AW minus dw AU, and then there's a commutator of AU and AW, right? But I just chose AU equals 0. So this component of F is super simple, right? The only thing that's in here that's non-zero is du AW, right? dw AU, that's 0. And the commutator is 0. It's linear in AU, right? So this thing is du AW. That is 0. Right? Okay, now that's great because it means that I can choose AW equals 0. What this is telling me is that AW doesn't depend on U, right? Now I'm free to make gauge transformations in this theory. I can make, I don't want to, it'd be a bit stupid to make a gauge transformation that kicks me out of AU equals 0 gauge, right? But the gauge transformation of AU is A prime U is AU plus du of some function, chi, right? So if I choose the gauge transformation function to be U independent, well then I don't change AU, right? So I can stay in AU equals 0 gauge and make a gauge transformation that is U independent. AW is U independent. so I can gauge it away, right? So now I'm left to a theory where I've just got, well, what do I got? I guess AW bar and AV, right? So those are the things we need to worry about. Yeah, so equation 2 helps with that. So equation 2 is, now you see this equation is, yeah, I've cunningly ordered these so that they get simpler. This one involves FUV. FUV is DUAV minus DVAU, that's 0, and it's got a commutator of AU, which I get to drop as well. So all that's going to be left here is DUAV on the left-hand side. On the right-hand side, I've got, well, now I've got AW equals 0. So this is a DW AW bar, and that's all. Okay. So these equations are integrability conditions, this last equation. So we can solve this by setting, so I could set AV. So if AV is dW of something, I'm going to leave a little bit of space here, I'll call it a little a, and AW bar is du of something, which I'll call A. Yeah. So now, if I put this in here, I'll get a du dw on the left-hand side of my A. And on the right-hand side, I will also get a du dw of something, right? So these equations are consistent then. So they're integrability conditions for the existence of this A. And somehow there's a factor of minus a quarter here, which makes things a little bit nicer. Doesn't really matter. Okay. And then finally, equation 3 becomes a proper differential equation for the A. So I'll leave you to work that out. I'll just write down the answer. So this becomes d squared A plus IG and a commutator. Okay, so that's it. That's the dynamical equation satisfied by this A. A is the only degree of freedom left in the theory. There's an action we could write down. So it's an integral d4x. Yeah, now let me see. So an action that we can write down just introduces an A twiddly, which is basically a Lagrange multiplier. D squared A plus IG, and then this commutator. dWA, dUA. That's our action principle. Now, the A twiddly is really what's left of the other helicity, the minus helicity. So there is a 2-point or a 3-point amplitude here with 1 minus and 2 pluses. That's what you'd expect from Yang-Mills theory. And there's a propagator which is off diagonal, propagates plus to minus. Right? So this is, this part is just a plus to minus propagator, and this part here is a 3-point. Actually, make myself a bit of space here. This is a 3-point vertex with plus, plus, minus. So the two A's are the two pluses. The minus is the little A twiddly. And by the, well, yeah, this maybe is an exercise that's worth doing. You can go ahead and figure out what the Feynman rule for this, actually evaluate this amplitude, 3-point amplitude. Well, the Feynman rule, there's just going to be, I've just got to differentiate the A, right? So let's say this is 1, 2, and 3. So this thing, there'll be a number which, is going to involve the G and some I's. Well, I have to differentiate these momenta, so I'll get P1W, P2U, minus, because of the commutator, P2W, P1U. Right. So in this quantity here, I'm going to give it a label. I'm going to call that X. X of 1, 2, X of P1 and P2. It's just some antisymmetric object, right? Some bracket made of these momenta. Okay, any questions so far? Yeah. Oh, question up here. Why Why did I add the negative helicity to the action? Well, it's just because if I differentiate, if I vary with respect to this A twiddly, then I get that. As simple as that, really. It's, in that sense, very naive. I kind of also know it's the right answer because this is Yang-Mills theory. I've just thrown away 1 degree of freedom, so, you know. I mean, there is another way of getting this, which might be a more satisfactory answer to the question. One could start with the full Lagrangian of Yang-Mills theory and select this gauge and go through this procedure, and you land on the same place. So, you know, I'm slightly shortcutting that rather. Well, it's quite a messy computation. Any other questions? Okay, well, one question you might have asked is, what gives? We know that the amplitude for 3 particles in Yang-Mills theory is not this weird x12. You know, it's the Park-Taylor. So, I mean, I think that I've clearly done something extremely weird. You know, definitely can't be changing the amplitudes. The amplitudes are well defined. This 3-point amplitude has got to be 1, 2 cubed over 1, 2, 2, 3, 3, 1. Right, so how the hell is it equal to x12, right? Well, they are actually equal. It's just a question of, you know, what I've done with all these choices of notation. So this is this plus plus minus amplitude. So recall, I guess Yaroslav probably talked about this last week, that when you're talking about this amplitude, these 3 spinners are proportional, right? Their brackets go away. That's why I've got square brackety guys here, right? In this convention, what I did here, sort of secretly, well, maybe, I guess what you can do is you can understand the relation between these 3 amplitudes by setting, by choosing a scaling of all of these spinners, right? The spinners of some scaling, this little group scaling, we can choose it at will. So I can choose it to set these things equal. So it's perfectly possible to choose a little group scaling so that these things are just equal. We don't usually do that because it kind of violates some nice things about the little group, like to think about it as being the little group for each particle. But you can't stop me from doing this, right? Then momentum conservation. So in a spinner notation, we can write momentum conservation like this. So this is just the outer product of these spinners. Right, so that is a lambda and a lambda twiddly. This is number 1. Lambda tilde. Right, so that's momentum conservation. Yep. Power 4, yes. Yeah, sorry. Wow. Yeah. Thanks. Okay, now since I've set these spinners equal, this equation implies that the tilde spinners sum to 0. Right. So then, so now if I take the product of this, so I come along with the 2, and I compute 1, 2. Well, 2, 2 is 0. So then 1, 2 plus 3, 2 equals 0. In other words, 1, 2 equals 2, 3 equals 3, 1. And the amplitude is just 1, 2. It's really important that I have power 4. Right, so that is the x12. So these are related. Okay. Somehow I like using the x when I'm writing things that are maybe Feynman rules. Spinners only really exist for on-shell particles, but this x thing defined that way exists for particles that are, doesn't matter where the momentum's on or off shell. Okay, very good. Now, well, another comment about this is that since these x's are closely connected to the spinners, we can use all of the results for spinner algebra to make the computations a little bit easier for us. And I'm going to use that. That's why I wanted to discuss this. Okay, very good. So now let's consider. Let's start talking about amplitudes in this self-dual theory. 4.3 amplitude. So, okay, so, well, so this 4.3, well, let's say it's like this. 1 plus, 2 plus, 3 plus, 4 minus. So let's draw out the diagrams. 1 plus, 2 plus, that's a minus, plus 3 plus 4 minus. This is another reason why I'm, you always have to have one minus outside when you're drawing these trees. It's easy to see that from a counting argument. 4 minus, 2 plus, 3 plus, 1 plus. 4 minus, 3 plus, 2 plus. Okay, so this is the S, T, and U channel diagram, right? So the numerator in the S channel, well, it's going to involve an X for particle 1 and 2. This is just this thing here, this X for 1 and 2. And then it's easy to see that it involves X, 3, and 4. I mean, from here, this X thing was, between the 2 plus helicity particles. So there's a plus here, it's bringing in momentum 1 plus 2, which is minus 3 plus 4. So there's an X of 3 and, say, minus 3 plus 4. So it's going to be X4, 3. With the minus sign, X3, 4 at the plus. So that's the S channel numerator. And all the other ones you get then by this permutation procedure. 2, 3, X1, 4. And U is X3, 1, X2, 4. Right. So NS plus NT plus NU, well, switching to the spinor notation, is just this sum, 2, 3, 1, 4, plus 3, 1, 2, 4. And that is 0 by the Schouten identity of spinors. So it just falls straight out of the Feynman diagrams. Now, yes? Yes, this is still self-dual. It's just because of this vertex here, right? The vertex always has this other particle on it, this minus guy. So the way I think about this is I'm taking particles 1, 2, and 3 and I'm shooting them in. Particle 4 is being spat out by the dynamics. Particle 4 gets spat out with a minus, as a helicity minus. So that's sort of what's going on here. This is the only amplitude I can build you see, these are the only kinds of tree I can build because I only have this vertex. I mean, the vertex it's just the same vertex as in Yang-Mills theory. You've got plus, plus, minus, you've got minus, minus, plus. That's it, right? This amplitude is indeed 0. Yes, this amplitude is 0. Yes. I was going to say that later, but you got to the point already. So, but it is indeed true that, well, so one way to see that is that the color-ordered amplitude, which is ns over s minus nt over t, that's 0. And you can go ahead and compute it. It's a straightforward calculation. Yes, so it's 0. It is, this is Yang-Mills theory, all tree amplitudes with all plus, if it's all plus trees, they're all 0. You can't even draw the Feynman diagram. It's essentially just 0 from the start. 1 minus are also all 0, the trees. The MHV amplitudes are the first one, 2 minuses and the rest plus, and then from there. Yep. well, I mean, it'd be hard to do, right? I mean, the kinematic terms in Yang-Mills are just going to be plus to minus. So integrating out, you'd end up with something non-local, right? You'd have 1 over d squares all over the place. Yeah, I guess that's, yeah. Even then, I'm not sure. Yeah. Okay. All right. So, well, it is true that the amplitude is 0, but nevertheless, let's continue. There is indeed a gravitational amplitude because of this double copy. There's a gravitational amplitude that we can write down. It is ns over s plus nt squared over t plus nu squared over u. So that is a perfectly fine amplitude. It is 0. And that's actually a little bit more tricky calculation, but again, it'd be one that would be interesting to do. It's more or less an exercise in spinor helicity. You see that this, yeah, you got to be a bit organized. Yeah, it's not too hard. Okay, now, it's not that every amplitude is 0. So there are non-zero amplitudes which are interesting. So let me, I'm slightly running out of time perhaps. When am I really supposed to finish? In 19 minutes time? Ooh, that's loads of time. Okay. Yes. Yeah, there's loads of questions. Good. So, no, that's fine. Excellent. There are non-zero amplitudes. There are loop amplitudes. In fact, the only non-zero amplitudes in this theory are at one loop. So an example would be at 4 points, one loop, say 1 plus. So this is genuinely all plus, 4 plus. And let's say this is plus, minus, plus, minus. So this is that's one diagram, right? So if I put a loop momentum here, this thing would have a numerator of, so let me say n box would have x 2 times that loop momentum, x 3. So this would have L plus P3, L plus P3 plus P4, L plus P, well, it's slightly boring, P4 plus P1. So this x here will have x P3 plus L, so just the L I can drop times x 4 L x 1 L. And that is the numerator for that diagram. There's a bunch of diagrams. Numerators of them are all made from these x's, and they will all satisfy Jacobi identities, even with the loop momentum, just because the algebraic properties of this x. Right? So you could double copy those, and you get the amplitudes in gravity. They're loop amplitudes now. You've got to do the loop integral. Okay, so this is a story where the Jacobi relations are more or less trivialized. The double copy just works, but of course I still haven't said, oh, where does the algebra come from, right? So that's the interesting question. Now, to understand where the algebra comes from, you have to look to gravity. Okay. So where does the amplitude, where does the algebra come from? So, so the answer really is in gravity. In this case, in self-dual gravity. So we have to impose the same equations or similar equations in gravity. So the self-dual equations in gravity are something like this: rho sigma. I guess I probably need a half epsilon rho sigma alpha beta is I. Something like that. I'm not sure about these factors, but something like that makes sense. Now, if you run through a procedure similar to the one I just outlined, it's more involved in gravity, and honestly, we typed it into a computer. You find that a very similar story holds. So, I mean, you choose a gauge, you choose, so we write basically the metric There's eta mu nu and a kappa h mu nu. Choose gauge, HU equals 0. And then you find a whole host of properties fall out of the self-dual equations. So you'll find that you can choose HU anything to be 0, and HW anything also can be set to 0 in analogy to the situation in Yang-Mills theory. You find that you can write the remaining degrees of freedom in terms of a prepotential, something you differentiate to get the H. You have to differentiate it twice. It was once in Yang-Mills theory. And you finally find an equation of motion. So there's 1 degree of freedom, one scalar field left. And the equation of motion, well, the equation of motion is known as the Plabansky equation. And d squared phi plus kappa. Now it has a Poisson bracket. du phi, dw phi. So the Poisson bracket here is defined in terms of these u and w derivatives minus dwf dug. So there's a Poisson bracket. Have I rubbed out the... let me see, I rubbed out the, so to Yang-Mills, we had d squared a plus, I think, so du a, dw a. So you could see that what the double copy is essentially doing here, the color kinematics replacement, is replacing the bracket of Yang-Mills theory with this Poisson bracket. So color kinematics. So it's this thing going to, there's some I running around. So replaces a commutator with a Poisson algebra. This Poisson algebra is an algebra of area-preserving diffeomorphisms. So the Poisson algebra so maybe not surprising that that the algebra is somehow related to diffeomorphisms. Now to see that, you replace w by define w prime as w prime of u and w, u prime as u prime of u and w. And I should say this is in u and w. So it's an area-preserving diffeomorphism algebra in these two dimensions. So then, this bracket is invariant, provided the Jacobian of the transformation is unity. So in other words, if you perform this differentiation with w primes and u primes instead of u's and w's, well then you'll get the same thing. The bracket of u prime and w prime will be the bracket of u and w, provided this Jacobian here between w and u, w prime and u prime, etc., is 1. That's the signaling, that's the area preserving requirement. Okay, yeah, so that's really what I wanted to say. It's time for questions.
Any questions?
Yeah. Yeah. So H.
Can you repeat his question?
Oh, yeah. So the question is, what's the relation between this phi and H? So yeah. So the relation is H is dd phi for the components of H that aren't 0 anymore. So those components will be, you see, set U and W equals 0, yeah. So for example, V will be dV phi. Yeah. Actually, when I think about it, it's probably a bit skew. So if you remember the way it worked for the A, it was something like AV was dW bar of my little a. So there's some funny mixing between the indices. So yeah, so this is probably not quite like that. But it is still the case that you differentiate the phi twice to get the H. Yep, yeah. So in exactly the same way as it arises in Yang-Mills, the remaining equations, self-dual equations, imply a dynamical equation for the phi. Yeah. So, okay. Yeah. Any other questions? Yep.
So the double copy is still a statement about derivative Q of t, but this is a case where you have some statement about the equations of motion that's clear. Do you
Yep.
learn something about the general double copy from
Yeah, that was always not as much as we'd hoped, I would say. It gets so you can sort of perturb away from this. So for example, the tree amplitudes in the self-dual theory are these single minus trees. They're kind of crappy because they're all 0. You can perturb away, and you can understand the MHV tree amplitudes from this. There is some slight limiting procedure that allows you to access the MHV tree. You need to include the other vertex. You see, yeah, so I had an action which just had one vertex. You need to include the other. There's some story. You can make that work. But as you get further and further away from the self-dual theory, like NMHV, it gets harder. There is, you can retrofit this story with the scattering equation. So the scattering equations is some technology for understanding amplitudes in d dimensions. There's a whole theory behind the scattering equations, but if you marry this with the scattering equations, then you can access any tree. But it's somehow marrying things which maybe don't seem like they're completely friendly. So I wouldn't say that really. I mean, you could certainly use this to write numerators for any tree with the scattering equations, and you can see that the Jacobi relations hold. But it's quite numerical somehow, or I don't know, you should get a lot out of it. That really doesn't seem to shine any light on what would be the kinematic algebra. People call this the kinematic algebra, the thing that computes the numerators by Jacobi identities. So in self-dual theory, the kinematic algebra is area-preserving diffeomorphisms. There are other cases where, the double copy can be used in various different places now. There are double copies for purely scalar theories. And there are examples there where they're not so different from this story, but where you can understand the diffeomorphism algebra, or sorry, I should say the kinematic algebra. But it's still an open question, and indeed, I would exhort you to think about this question. Bring new ideas, that would be great. We don't really know what the kinematic algebra is in Yang-Mills theory. It would be fantastic to understand it in more detail. This is a consequence of the gauge choices we're making. Yeah. So we're definitely putting the theory, we're picking particular gauges. We're throwing away some things you might care about, like Lorentz covariance. Completely throwing those away in order to try and make this particular structure stand out. This gauge, so if you have a self-dual solution, the gauge is generic. So you can always put the theory in this form for a self-dual. Question? Yeah. Okay, so I guess the question is, can we think of other situations where there's interesting classical dynamics that might have a double copy structure? So there are some very creative people out there who have figured out systems. There is sort of a fluid dynamics type system. It's kind of an interesting one where The double copy is sort of a tensor fluid, so it's kind of a crazy thing. But yeah, I mean, there are, again, it's perhaps not so unrelated to this. There's some sort of you can think of these equations as being a little bit like the Navier-Stokes equation somehow. There's some potentials, some derivatives. So it's not a million miles away from this self-dual story. But yeah, there are some very interesting examples of things along those lines. And maybe some other ideas on how to make this kinematic structure more transparent, by thinking about currents, rather than field equations and things like that. Yeah, I mean, that actually has been a promising and fruitful line of research. Yeah. Any other questions? Yeah. Yeah. Interesting question. So I'm going to talk about Kerr-Schild. So I guess the question was, can we put this metric in Kerr-Schild form? I'm going to talk about Kerr-Schild metrics more in this lecture because there's definitely a connection between Kerr-Schild metrics and the double copy. These particular solutions aren't Kerr-Schild in a traditional sense. But so the Kerr-Schild metrics have the structure. Let me see, to answer this question, I need to write an equation. So Kerr-Schild metrics so the metric, the exact metric would be something like G mu is eta mu nu. And since I'm doing exact stuff, no need to put a kappa. H mu nu, where H mu nu is the form K mu phi. And these K's satisfy various identities like K squared equals 0. K mu, K nu, K per mu. Okay, so this is the Kerr-Schild story. I'll say a little bit more about it in a later lecture. Now, so here the K mu and K nu in Kerr-Schild are vector fields. However, from a scattering amplitudes point of view, it's very reasonable. These things they look like they want to be momenta, right? Now, momenta. So phi here is something that lives in space-time. So if you think of these K's as being something that are like momenta, well, momenta then are linear differential operators. So if you permit me to make these K's linear differential operators, then indeed this story fits in. Yeah. Excellent.
Well,
right.
let's
that was
let's go for it.
Good place to finish. Huh?
Yeah.
Yeah.
Let's thank Donal. So
Thanks.
coffee break. We'll be back in a few minutes, guys.